So in the last couple of videos, we talked about setting the unit system and accessing properties for real fluids inside of ease. And in this video, we're just going to do a real simple example that shows how to use these properties to solve an engineering problem. So our problem is shown here. It's a vapor compression cycle. We're going to assume that the working fluid in the cycle is ammonia. The ammonia is going to change state as it circulates through first a compressor and then a condenser, and then there's this throttle valve, and then finally the evaporator. And the cycle is providing refrigeration to a low temperature reservoir at TC, which we're going to set to 260 Kelvin, and rejecting heat to a high temperature reservoir at TH, which we'll set to 320 Kelvin. So as we talked about previously, before I access any of the properties in ease, I have to set the unit system. That's very important, and we'll do that here with a $UnitSystem Directive. So I'm going to have my units set to SI units. I'm not using any trigonometric functions, but if I were, I would have arguments in radians. I want all of my specific properties to be on a mass basis, energy in joules, pressure in pascals, and temperature in Kelvin. And then I'm going to go ahead and enter the two known temperatures. So TH is 320 Kelvin and TC is 260 Kelvin. The refrigerant is ammonia, so if I want to understand what the various models that are related to ammonia are in ease, I'm going to go ahead and open the substance information dialog here, and I'll search for ammonia across all the available fluid models. And there's a few here. Some of them aren't relevant. They're ammonia water mixtures and so on. But you can see that the real fluid model of ammonia is designated by the fluid ammonia, right? Or alternatively, the fluid R717 is the same thing. So let's enter that fluid name as a string variable so that if I want to, I can change refrigerants only just by changing the value of the string variable. So $R equals ammonia. And then let's go through the cycle. So we're going to assume this is a very ideal cycle. So as a result, the refrigerant leaves the condenser here at state 4 as a saturated liquid, so it has quality of 0. And the approach temperature difference is 0, so it's going to leave here at the heat rejection temperature. So I'll enter those two known properties. T4 is TH and X4 is 0. And these two intensive properties fix state 4, which allows specific entropy, pressure, and specific enthalpy to be determined using the property functions. I guess it would be entropy, pressure, and enthalpy respectively. And the indicators that I need to fix the state are going to be T equals and X equals, since I know the temperature and the quality. And if I solve at this point, you can see now that the fourth element, the fourth row of the array has been filled in because I'm working on state 4. And it's worth going ahead and setting the units of these variables and verifying that I don't have any unit issues before I move on. So the other state that I know right away is the evaporator exit state, so state 2. So here we're going to assume that the evaporator exit is saturated vapor, so the quality is 1, and that it's leaving at the refrigeration temperature TC, so the temperature is also known. And again, these two intensive properties fix state 2, so I'll go ahead and get entropy, pressure, and specific enthalpy again, and the indicators are again T equals and X equals. So the fluid leaving the condenser at state 4 is expanded to state 1 in this throttling valve, and the valve is isenthalpic. So the specific enthalpy at states 1 and 4 are equal, so I know the enthalpy. And then we'll also assume that there's no pressure loss in the evaporator, so that the pressures at state 1 and 2 are equal, so P1 equals P2. So I know H and P here, which fixes state 1, and that allows us to calculate the specific entropy and the temperature. And of course the indicators are H equals and P equals. The fluid leaving the evaporator is compressed to state 3 in a compressor that we're going to assume to be reversible and adiabatic, and therefore the entropy at state 3 must be equal to the entropy at state 2. And again, we're going to assume there's no pressure loss in the condenser, so the pressure at state 3 and 4 are going to be equal. And so entropy and pressure then fix state 3, so we'll go ahead and get enthalpy and temperature, and again the indicators are going to be in this case S equals and P equals, since I know entropy and pressure. And if I solve at this point, you can see that all of the properties at each state are conveniently organized in this arrays table. So I can just go through and look at states 1, 2, 3, and 4. I can do energy balances on the condenser and the evaporator and the compressor. We're going to do them on a per unit mass basis, and that will give us the rate of heat transfer from the condenser and to the evaporator, as well as the rate of work transfer to the compressor per unit mass of refrigerant that passes through them. And that's just these differences in enthalpies. And then finally, if I want the coefficient of performance for the cycle, that's just the ratio of, in this case, the evaporator heat transfer to the compressor power. That's COP. And I can solve and see the COP right here. All right, let's do just a couple of other things, as long as we have this model working. The first thing is, let's show how to make a property plot. So let's see. Let's get this up so we know some of the useful pressures here. And temperatures. So if I want to make a property plot, I go to plots and then property plot. We're interested in ammonia. We could do a TS plot or a pH plot. I think we'll do a TS plot. And we'll include these lines of pressure. So you can see that the two pressures that are probably pretty important to us are 255,361. That's the evaporator pressure, and 1.872 E6. That is the condenser pressure. So we'll make sure we have those. I don't need lines of constant specific volume. And we'll hit OK. And then if I want to overlay my states, overlay plot, let's see, the x-axis on a TS diagram is S, and the y-axis is T. We'll make these big red and add some point labels and hit OK. And you can see here 1, 2, 3, 4. Those are the states in my refrigeration cycle, which is really nice. The other thing I can do is I can change the refrigerant. So I did ammonia here. I could probably change this to something like let's try R134A. And because I'm using this string, it will change the refrigerant in every property call. So if I solve, you can see that the new COP is 3.079. So R134A, at least theoretically, is not quite as good as ammonia in terms of being a refrigerant, at least at these temperatures. And the last thing that's kind of interesting is to make a parametric study. So maybe I want to know, how is the COP varying with TC? So I would make a table, and in the table have COP, and then also have TC, and hit OK. And let's vary TC from, I don't know, 260 to 300. Oops. And hit OK. And of course I have to comment this out here, or put a $if parametric, and then I'll go back to my parametric table and run it, which is this green button. And you can see this is how the COP varies with TC. If I want to make a plot, that's pretty simple. TC, COP, and hit OK. So yeah, this is a nice illustration of how to use the property functions in ease, and then some of the other sort of associated features of that.